So I'm Leevar Williams. I'm an engineer on the developer operations team here at AppNexus. And I'm here to talk to you about test environments today. So before I explain what I mean by that, I'll briefly talk about what we do here in the DevOps team. So DevOps has become somewhat of an overloaded term these days in the industry. It means something slightly different depending on who you talk to or where you are. At AppNexus, the DevOps team is charged with accelerating the pace of software development by providing tools and systems that enable others to produce code as quickly and effectively as possible. So this means we're primarily an engineering team, and as such, we spend most of our time developing software ourselves. So most of the engineering teams here deal with pretty complex systems at a very large scale. So if you've been to some of our previous tech talks, you may have heard from the team that develops our real-time ad serving platform. And their system needs to handle millions of requests per second at peak. Or our data platform team, whose aggregation pipeline processes and ingests hundreds of terabytes of data per day. So we're not here to talk about any of those exciting, highly distributed, large-scale systems today, or at least not directly. What we're talking about is a slightly different type of scale, which for DevOps usually presents in the form of organizational or operational complexity. So one of the biggest pain points that our organization has had to deal with in recent history is the testability of our platform. And rather, the lack of a good way to test end-to-end in a stable, reliable, and isolated way. And the biggest question was always, how do we test a platform that's as large and complex as ours? So a few years ago, the DevOps team realized that this is a problem that falls squarely within our domain. It's complex at an organizational level, and the solution probably required us to write some software. So as we set out to solve this problem, we stepped back a bit to consider, what's the problem that we really need to solve? It's not really how do we test. The question really became, how do we enable our organization to reliably produce quality software? So, in the end, we developed a solution with that in mind, and we built an infrastructure around how test environments are created and delivered for the AppNexus platform. And this really enabled our organization to test, develop, debug, inspect, and manipulate our platform in ways that weren't really possible before. So I'll talk a little bit more detail about the problem and the motivation behind it. Why was this a problem worth solving? Then I'll talk about our solution, how we came up with a way to solve this, and some details about the architecture behind it. Then the outcome we saw from this and some lessons learned along the way. So what do I mean when I say test environment? There's a more general definition than what I have up here, but this is what I'll be referring to when I say test environment. It's something you might also call an integration or a staging environment. And in theory, it's a functional replica of your production environment, but a completely separate from the production system itself. So to really understand how you might leverage a test environment and why it was particularly difficult for us, let's step through a simple example. So let's say that you have a very basic web application stack. You have a database, an API web service that sits on top of it, and a front end that serves your actual website. So because we're reasonable engineers and we don't just push directly to production and hope for the best, we create another environment. We call it stage. So in theory, these two environments are functionally identical. They're running the same code. They have the same database schemas, but they're configured slightly differently. There are different hosts involved, different components, and there may be different sets of user data. So the idea here is when you push new code to production, you'll first push your stage environment. You may do some basic tests. You want to make sure that your deployment works, that your service comes up successfully, and you may have some basic smoke tests that you run. And if all's good, you then push your change to production. All right, great. So since there are multiple developers who are developing interdependent components, there are bound to be collisions at some point. So let's say someone on the API team has just developed a change and they want to release it to production. First, they push the stage, but there's a bug in the code, so they break the API. This is actually great. This is exactly what we have this for. We pushed code to our pre-production environment. We ran some tests. They failed, so we didn't push to production. Great. But me, as a front-end engineer, I'm also developing a UI change. And when I attempt to push it, I see that my service is no longer working. However, I also knew that it wasn't working just before I pushed the change. So since the API is my only upstream dependency, I know that someone on the API team must have pushed a bad release. So I get up, I go grab a cup of coffee, and by the time I come back, the API developer has backed out his bad change, and I can now push my code change to our staging environment. So let's make this picture slightly more complex by adding in 2 more use cases. Let's say that we are developing a large new feature, and it's going to require changes all across the stack. So to the database, to the API, and to the UI. It's a cross-team development effort, and we're still in the early stages of development, so the code is far too risky to release to production in any form. But we still want to be able to, we still want some sort of test environment to be able to test this interaction between components as they're being developed. So since we have a fairly basic stack, just 3 components, it's easy for us to just create a new environment. Let's call it sand. And this sand environment is now being used for this cross-development effort. And we have another test environment that is separate from our staging environment, separate from production, and all is well. So sometime later on, the product team comes to engineering, and they say, we have a set of clients that we would like to offer a testing environment to so that they can experiment with different settings, different configurations, without impacting their production integration. We also have some new features that we want to demo to them. These features haven't been released to production yet, but we want a stable environment where we can sort of sell the new features to the product that are going to be released at some point. Okay, so we're getting good at this now, so create another environment for client testing and integration. So now we have 4 environments, 3 used for testing and development, and 1 production. And they're pretty cleanly separated by use case. But as we're a growing business, things don't quite stay this simple. So assuming we're a successful company and we're growing quickly and going after new business as fast as possible, there are a few inevitabilities that are bound to happen to our system. One is, as we grow, the system is going to get more complex. More components means more interdependencies, and creating a new environment is no longer a simple task, and it becomes a very long, time-consuming effort. So this severely limits the number of test environments that we have available to us, just because the time involved to create one it's so much larger now. Also, developer headcount is going to increase. So more engineers means more people writing more code, deploying more frequently, and there's more demand for these sort of full end-to-end test environments to satisfy these development and testing efforts. So now, we have a limited number of environments, yet the number of use cases for them is growing and have surpassed the number of environments we have available. So people begin to share. In general, sharing is a good thing to do, but not when you're talking about environments like these, because collisions like the ones I described earlier are bound to happen, and they'll happen a lot more frequently, and ultimately still the pace of development. So there's a corollary to these 2 points, and that is the likelihood that the deployment of a change to production will introduce an inconsistency or breakage into a non-production environment approaches 1 as your organization grows. So this means no longer do we have this nice homogeneous set of environments that we started out with. We actually have something that looks like this, where there is now a high degree of divergence between production and non-production. So this isn't quite the hypothetical story I was making it out to be. AppNexus was actually in a similar situation to this maybe 3 to 4 years ago. One key difference here is that our system doesn't really look like this. It looks more like this. So imagine this platform applied to what we have here. I didn't attempt to actually detail all the differences in the environments we had, but I'm sure you can imagine that when we're talking about a platform of this scale, the use cases become vastly more complex than my simple example. So we ended up with a system that was very hard, if not impossible, to truly test end-to-end. And that's not a good situation to be in. We saw quality go down, unreliability go up, and ultimately the pace of software development, developing quality software, it slowed, and we saw this sort of stagnation. So, given the mandate of DevOps that I described earlier in the talk, this was a trend that we needed to reverse. So we knew that the existing paradigm here, this definitely wouldn't work. We needed something better, but we weren't quite sure at the time what a solution looked like. So we went out and talked to our stakeholders and started gathering requirements. And one thing we noticed is that the use cases we saw, there was a pretty broad spectrum of use cases for test environments, like what I described, but there were a few common themes. I think all the use cases we heard, almost, were some variation of this. Users want to be able to clone some portion of the current production system, change its state in some way, and then observe the resulting behavior. And this applies as equally to testing as it does to developing against your dependencies or reproducing a bug in production, supporting a client or handling a client support case, demoing a new feature. It's all sort of centered around the same core requirements. So in doing this, we came up with a few requirements of our own. To be able to provide something that would provide our users with this need, we need to know a few things. We need to know what production looks like at a given point in time. We also need to know how to recreate production, or at least a subset of it, as an isolated test environment. So we knew from just prior experience that it's very hard to maintain a persistent set of environments and keep them up to date with production by continually upgrading them as production is upgraded. It doesn't work, and it results in the type of divergence that we saw earlier. So given that we know how to create one, we might as well just do that n times and never have to have a set of long-lived environments that we try to keep up to date and spend a lot of time doing, but ultimately fail at. Third, we need to enforce a standard mechanism by which applications are configured and deployed onto our platform. If we don't have this, then 1 and 2 become very hard as additional components are introduced into the system. And then finally, we needed to ensure that the underlying infrastructure can deliver these test environments to any user in an on-demand fashion. So we knew a lot of people wanted this. They wanted many environments, and they would want them quickly. Okay, so to digest this into a high-level requirement, this is really what it was. We needed production-like test environments that are produced by an automated service at scale and made available to the entire company. So before we did anything, we needed to name this. We needed some way to refer to these types of environments. So we call them auto environments. If you ask anybody here how they develop or test, they'll probably say with an auto environment, or AutoM for short. So there's a lot going on in this statement. So let's unpack it a bit. I'll talk through each of these points. First, we need to be able to create production-like environments. Like I said before, that means we need to know the state of production at a given point in time. So there's a few things here. I won't go into much detail, but suffice it to say that these were actually very hard problems to solve. But I'll just quickly go over them and then get to the interesting stuff. But to be able to know the state of production, we need to track a few things about our system. We need to be able to track changes to database schemas, which applications depend on. We need to be able to reconcile differences in configuration between production applications and their counterparts in a non-production environment. We need tracking around deployment logic, and also just sort of one-time bootstrapping and initialization steps that are involved in creating a new application instance or a new cluster of things. So next, we need to be able to do this at scale. Most of our production services actually run in VMs. We run some workloads in bare metals, but in terms of distinct number of services, most things run in virtual machines. And all of our production services are configured via Puppet, which is a configuration management framework. So provisioning a new application instance requires a VM or bare metal to boot up, and then a full Puppet run. But this works pretty well in general. But given that we have about 80 components that make up our platform, and we need to be able to do this quickly, booting up a VM and installing a bunch of software on it is not necessarily a cheap operation. So it's a process that might take 10 or 20 minutes or more. And we knew that if we were to do this as frequently and with as much concurrency as we wanted to, it would be very costly in terms of the amount of strain that would put on our infrastructure. So we needed a better solution. We started looking at Docker. So for those of you who aren't familiar with Docker, this is a company whose main open source product is called Docker Engine. And Docker Engine basically takes advantage, it's a piece of software that takes advantage of some existing kernel functionality to produce containers. And containers are basically lightweight virtual machines. They have their own process space, their own networking stack. They can run separate sets of libraries and binaries, but they share the same underlying kernel of the host. So that's good. They're very quick to start up and tear down. Another thing that Docker actually gives us is the concept of a layered file system. So each container has its own view of the file system. As changes are made, more layers are sort of stacked on top of each other. And those layers together make up an image that you can use to create another copy of that container. And these images can be pushed to a central repository, Docker registry, and then very easily distributed to another host. So we have container X, we want to run it somewhere else, we can commit it, create an image out of it, push those layers up to the registry, and then pull them down on a different host and have another running copy of that container. So this is perfect for us. We had almost zero boot time. We could pack these very densely because there's no overhead as you would have with a typical virtualization framework. And we can easily snapshot and distribute containers amongst a large set of hosts. One of the problems was we started looking at this back in August of 2013 when Docker was still in version 0.6. So it was definitely not mainstream yet. Still beta, very immature. Yet there was a sort of a good and growing, very active community around it. But this also meant that a lot of the tooling and frameworks that are now natively supported by Docker, things around easy host provisioning and high-level orchestration about how containers can be launched together and linked to each other, and managing a set of containers across a fleet of physical servers. None of these tools actually existed when we were building the system. You notice the difference in dates there. So we ended up having to build a lot of these systems ourselves, or at least the functionality that these provide. OK, so this is great. With Docker as the core piece of underlying technology, we began to architect the system that would fulfill our high-level requirement, delivering test environments quickly and at scale. And this is what it looks like. So I'll zoom in on a few of these pieces so we can really understand what's going on here. First, let's look at the container management piece. So as I mentioned before, we're running Docker across a number of physical servers. And in order to manage the containers across them, sort of in one central way, we built an API layer on top of it. And this API layer exposes a lot of the high-level container operations and operations around pushing and pulling images from the registry. We run a copy of Docker registry as well. We also ended up building a scheduler that basically knows how to place a container given the set of resource constraints. So things like memory, disk, IP availability. Whenever a container needs to be launched, the scheduler will figure out where within its infrastructure that container can be placed and then do it for you. So another thing that Docker didn't support right out of the box for us was networking and service discovery, or at least robust support around this. If you think about what we need to do, launch environments, which are collections of containers, those containers need to communicate with each other, and they need to know about each other. If you don't have these two things, you can't really do that. So we had to figure out how to do it. To understand that, let's dig in a little bit and really understand how Docker does networking in its default mode of operation. So this is a Docker host. We have two containers here. When the Docker application starts up, it creates a network bridge, which is basically a routing interface between the container network space and the underlying host network space. So this is a Docker bridge, Docker 0. And it chooses a subnet, a private IP space, and for each container that it creates, it assigns an IP address out of its IP space to the container, and it creates a pair of virtual Ethernet interfaces. One gets thrown into the container, and one remains on the host itself. And when you have several containers launched this way, networking works pretty much as you would expect. Container X can communicate with container Y by referring to it by its IP address. And traffic sort of flows through the bridge into the other container, and that all works very well. This doesn't work if you have containers that need to talk to each other cross-host. Containers on another physical server that need to communicate with these containers. So there are actually a couple ways you can do this, and both of them take advantage of NAT, or network address translation. So let's take a look at how that actually works. One way you can do this cross-host container communication is by telling Docker to create port mappings, basically, between the host's external IP address, 10.0.0.10, which is externally routable, meaning another host can find it on the network and talk to it. Mapping between that and the container's internal IP address. If you don't know, these IP addresses are actually internal to the Docker host and are not externally routable. So if you do this port mapping thing, then what Docker is doing is basically setting up an IP tables rule for you. So this is saying for traffic from any source and destined for 10.0.0.10 on port 80 to container X's IP address on port 80. So this is good, but the only problem here is that these IP address port pairs actually have to be unique. So if you have 10 containers running on this host, all of which need to expose a web service on port 80, you can't actually do it because the underlying host only has one external IP address, and you can only map to its port 80 once. For the rest of the containers, you'd have to use some other port. It would get weird, and it would just cause a lot of confusion, get really hairy really quickly. Alternatively, what you could do is associate many routable IPs with your Docker host. If you do it this way, you can still do port mapping, but instead of having one external IP address onto which you're mapping container ports, you can actually create a pairing between each container and one of the external IP addresses. So in this case, we have two rules. So say I want to expose port 80 on each of my containers, I map each of them to a different IP address. And each one now has its own externally routable IP address and access to the full port range. So that's a little bit better. So, and this is actually the initial implementation, how we decided to do networking at the beginning. There are a few problems with this still. One is that now we have to, since we have multiple IP addresses mapped to each Docker host, and we have many physical Docker hosts, we now have to do this additional layer of bookkeeping. And we need to know which IP addresses map to which Docker hosts. This is fine, but you can end up in a situation, if you're not careful, where a particular IP address is mapped to more than one host. This produces all sorts of weird networking behavior. It's extremely difficult to debug. And it's really just sort of creates another headache if your bookkeeping isn't, some error in the logic or just doesn't work as well as you think it does. Another problem, which is actually the deal breaker for us, is that we found that outgoing traffic from containers, you have this container X that needs to talk to another host externally on some other host. Packet traverses these bridges, goes out the external network interface, but it has a source IP of the container's internal IP address. That means the host that receives that packet thinks that it came from 172.17.0.2. But that means nothing to anything that exists outside of this host. And generally, this wasn't a problem, but it made a difference for things that do their own sort of service discovery, like Hadoop's an example of that. There are actually ways you can get around that, but we decided to go with a simpler solution. What we ended up doing was actually creating our own custom bridge. So instead of having Docker create a Docker 0 bridge, we create a custom network bridge. And then we disassociate the host's external IP address with its main network interface and bring it over to the custom bridge. And then we start Docker with this set of parameters with its own range of IPs that it will then assign IP addresses from to its containers. So now, these containers they actually have externally routable IP addresses, and none of the IP table trickery that I showed you before has to happen. And it works very well for us. Another thing we need to figure out how to do was service discovery. And this means when you have a collection of containers that need to be able to talk to each other, now we know that they can talk to each other if they live on different hosts. But how do they know about each other's existence in the first place? And there are a lot of sort of software solutions around this problem, things that create overlay networks, but it really adds a lot of overhead and a layer of complexity that we weren't prepared to deal with. So we went with a very simple mechanism, just DNS. All of our containers have this sort of canonical host name, which is made up of 4 pieces. First is the host number. Second is the application that the container is running. You have the name of the environment the container belongs to and its data center. If another container in this environment needs to refer to the API container, if we put a little bit of convention over this, we can easily create a DNS record that maps this name, so host number, application, environment, and then append this .envnexus.net suffix. Now we always know, given an environment name, how to refer to a particular container in that same environment. Okay, so now that we've sort of figured out some of the low-level details of this implementation, let's look at some of the other pieces in this infrastructure here. So I mentioned before that there are things like Docker Compose that allow you to orchestrate how a set of containers is launched and how they're connected to each other. Again, we didn't have that, so we built our own. We have a notion of environment templates, which are basically they're simple JSON files that contain a set of entries, each of which describe a container. So in this little snippet right here, we have an API container. Its host name is right there. We can impose resource quotas that are used by the scheduler to place the container, define the base image it's going to be launched off of, and give it a list of requirements. This imposes an ordering constraint over how containers in the environment are launched together. We also have a configuration management API, and this really serves 2 purposes. One is to allow us to capture the state of production. So that means things like the state of the various data stores in terms of schema, the versions of applications that various components are running, the versions of the configurations that they're running, et cetera. Second purpose is to keep track of every container that belongs to an active environment. So with those 2 things, we have the environment launcher, which basically does all the heavy lifting around how an environment is actually created. So its only input is the name of a template, and its output is a live functioning environment that conforms to the specification of the template. When it launches an environment, the final step is just to do some basic verification. It wants to know that all the services it launched are running, that DNS resolves and the containers are reachable, and that the basic functionality works. And if all of those things are okay, then that environment is sort of stamped as verified and made available for consumption. Okay, so the last piece here that sort of ties all this together is Jenkins. And we really only use Jenkins for its scheduling functionality. We have a set of things that needs to run at a defined interval, and if something goes wrong, we just want to know about it. We want to get an email notification. So these are things that Jenkins does very well, so we decided to use it. These are the main workflows that we run out of Jenkins. First is actually very important. On a daily basis, we need to capture the production state. If you remember, at the beginning, I talked about the requirements for us to be able to build a service that delivers test environments. this was the main one. We need to know what production looks like. So every day, we have some logic that actually goes out to production and asks it for its state. All of that gets sort of shoved into our configuration metadata store. And that becomes the set of versions and configurations that are used to launch the next set of environments. Another thing it does is ensure environment availability. So the templates I mentioned, each template sort of describes a different collection of containers, which means we can do things like provide environments that are geared towards API web service development, or geared towards the development of our ad serving platform, or the data platform. We have a number of templates, and associated with each one of them is a limit. How many of that type of environment do we need to have available at a particular time? And all Jenkins does in that case is it pulls the configuration service, figures out what all the active environments are, asks, do I have enough of this particular template? If not, it'll invoke the environment launcher to launch n number of environments to satisfy that constraint. So that runs continuously every few minutes. And then finally, as environments expire or the resources are released, we just have a job that pulls every few hours that goes and reaps all the old containers, reclaims those resources so they can be used for new launches. Okay, so now we actually have an infrastructure that can create these environments quickly and in relatively large quantities. Now the final piece is we need some way to be able to deliver these to our end users. So we wrote a very simple CLI tool called AutoEnv. And it's a command line tool. Anyone has access to it, and it actually has a lot of functionality built into it, but two primary functions. One is reserve. That's the user saying, hey, I want a new environment because I have something to use it for, whether it be developing a new feature or testing, what have you. And this will go out and find an environment and tell the user, here's your environment. The second function is release. This is the user saying, hey, I'm done with this environment. You can have the resources back. So we schedule it for deletion, and it gets reaped within about an hour or so. And then those resources are recycled, allocated to a different environment. So the CLI is actually a very thin client around an API. The API talks directly to the container management API and the config management API to figure out, do I have an environment of a particular type available? What are the containers associated with it? And for deletion, it'll actually just schedule the containers for deletion when the environment is released. So we released a basic version of this a couple of years ago now, and we've really seen usage take off. So this is a graph of monthly environment reservations. Starting about 2 years ago, May 2014, ending in April. And you can see there's sort of an inflection point at the beginning of 2015 where people just really started reserving a lot of environments. Some other numbers here. To be able to support this type of growth, we had about 300 unique users, and about 40% of those are regular users. So that means within a given month, they have at least one environment reservation, 1 new reservation. We have about 200 bare metal Docker hosts behind us, and at any particular point in time, we have about 10,000 active containers. And over the lifetime of our service, we've launched far in excess of 1.5 million containers. So what we saw happen is like a lot of use cases opened up. We saw a lot of things happening across the organization that we didn't necessarily anticipate when we first developed the service. This is just a list of the use cases we've seen. We've worked very closely with our engineering quality reliability team to allow them to automatically run an end-to-end platform test suite on every release to our API or ad serving system, which has been fantastic. We also have seen these used for testing and development of new Hadoop jobs in our data platform. They're used by operations for testing OS migration. We've seen use outside of engineering by sales. They want to be able to demo new features to clients, change our product in certain ways that wouldn't be okay in production, and use these environments as tools to sell. And the list goes on. We've seen them used for client support case investigations, onboarding external bidders, and integrating them with our platform, and just as general stand environments for new clients or for existing clients. So there are a few lessons learned along the way in developing this system. I think one, and the most important, is act early when it comes to scaling your organization. We saw signs of the stagnation that I talked about fairly early on. Knew it was a really big problem, but had we sort of acted on solving it earlier, it may not have been as difficult as it was in this case. So it's definitely important to sort of observe these signs about ways in which your organization is not scaling and address those. Also set clear user expectations. As we were developing the service, in the early days, it was actually fairly unstable. Containers would sometimes just disappear or services would go down, and our users who had now come to depend on this for testing or developing or doing their job will just come to us and say, hey, why is my environment down? And we tell them, like, we know we're fixing it. There are a lot of things here we need to figure out. We were sort of, changing the engines out as the plane was flying. So I think one thing we could have done better is sort of being more explicit with our users, saying that, hey, there's this thing that you can use. It's not completely stable right now, but tell us where it breaks, and we'll fix it. Also, be aware of operational overhead of new technologies you adopt. So Docker was a new technology that we brought into our ecosystem. We made the conscious decision to bring in an immature technology, relatively, into our platform, but didn't necessarily know the operational overhead we'd have to deal with. We actually learned a lot about operating a fairly large Docker infrastructure, and have spent more time than we would have liked debugging kernel issues and networking bugs. So you should, at least even if you make the decision to do this, definitely be aware of the sort of hidden overhead that happens when you adopt these types of technologies. And lastly, I'd say design for scale, implement for speed. So I think the first part is pretty obvious. You obviously want to design your systems such that they can scale without sort of a large refactor. But in this case, it's not necessarily always the right answer, but we decided to go for speed. We had a design in mind, but we cut some corners. We decided to incur some debt so that we can provide this service more quickly to our users. I think as long as you're aware of that, it's sort of okay to do. That's all I have prepared today. Thanks for listening. If you have any questions, we can take those now.
Hey, nice talk, thanks.
Thank you.
You mentioned you started using Docker before all these other tools were available. If they were available, how would it have changed things?
Well, we probably would have had to do a lot less work. I mean, a lot of the tools that are now available solve a lot of the operational pain we've had to deal with. In particular, things like Docker Swarm, which allow you to sort of do this networking and magic around managing containers across hosts. There was no native support for that, but we absolutely needed it, so we had to build it. If we had something that did it for us, we wouldn't have had to do it. I think that holds true for Compose and potentially Machine as well. We have a set of provisioning scripts we've written to sort of configure hosts in a very particular way. And if we had other tools to do this, we probably would have been able to focus more on the software itself rather than the operations.
I see. I was just curious because I was wondering, there were like two parallel tracks of development happening, and I was curious how similar they ended up happening. So yeah, I guess very similar is the answer?
Very similar.
Okay, thanks. Yeah.
I'm curious about the end-to-end platform test.
Yeah.
Are you guys building testing using real services and real containers, or you build mock service and more lightweight containers during the end-to-end platform test?
So the question was, as it relates to end-to-end platform testing, do we test against real services and real containers, or do we mock services out? So the idea is, like, in order for it to be a true end-to-end platform test, we want to do we don't want to do very much mocking. we want to test the actual services, the actual code paths that are going to be hit in production. So we test against the actual code, the actual services, but not production services. The idea around test environments is that we replicate production, have the same services running, similar sets of data, and run tests against that. But the idea is that it is a functional replica of production, so we're testing against actual code.
Hey, how are you? I just wanted to find out, how do you handle the data for testing? So if I write some code and I want to run a test against 100 gigs of data, where's that data coming from?
Yeah, the question was, how do we handle data for testing? It's actually a very good question. So that can mean a couple of things. At the most basic level, what you need, certain applications require a very minimal data set to be able to function. So this might be things like data you have in lookup tables or enumerated values, things like that. We do track those and pull those in test environments. If you need to test against actual production data sets, this is a use case we've actually heard of. People do this. So what we've done is, in the environment templates that I mentioned, we have a template that's geared towards testing against a production data set. So we basically snapshot our production MySQL databases, create images based on those, and pull them into test environments, launch the services around that. So you actually have an environment with your production data set that is separate from production itself.
And how long does that take to bring up?
Another good question. How long does it take to bring up? Well, there are a few steps involved. First, this is MySQL. We need to restore the MySQL backups. That takes, this is hundreds of gigabytes of data in some cases. Takes several hours. Creating a Docker image base out of that takes another maybe 3 to 4 hours. Once we have that, we don't distribute these to the Docker registry because there are hundreds of gigabytes in size. We actually just create them in place on the servers where the workloads will be launched. Starting up a container based on the image is very quick. It's almost 0 time.
Thank you so much.
Yep.
Great presentation, by the way.
Thanks.
So how did your team coordinate with the QA team as far as running automated test suites? What test suites did you guys actually use, especially with automated unit integration, regression tests, things like that?
Yeah, so the question was, how did we coordinate with the QA team to sort of develop and automate these tests that run? So the QA team was actually our very first customer. I think there was most of the demand was coming from them. They had their own sort of homegrown framework for writing integration tests that are specifically geared towards our platform in terms of how objects are created and then auctions are run against them. So they had a framework. They already had a set of tests. And we basically just worked with them very closely to make sure that the environments were stable enough and performant enough and functional enough to actually run their platform tests. And since then, they've sort of incrementally built things out. And we continue to work very closely with them as they add more functionality, depend on more services, et cetera.
Got it. Second question. So did you guys have any platform or software that was license-based, even with lower environments?
Do we have any platform or any software that was license-based? Yes. So there are a few things we use in our platform that are not open source. One is Vertica. The way Vertica is licensed, we pay per unique data. So since a lot of the data we're generating in test environments is not necessarily unique, or we're not generating very large amounts of unique data, it really is not a problem. I think that's probably the only piece of licensed software that we launched in test environments that comes to mind.
Okay. Yeah. So at my company, we have a CMS that every environment that we build out requires its own license. So I'm wondering if we applied that auto environment system and idea to that, if what kind of roadblocks you might hit if you've already sort of gone through that.
Yeah, it's actually not something we've had to deal with at all. Most of the stuff we use is open source technologies. We have a few that are license-based, but we haven't had to deal with having to create licenses for test environments, at least not at this point.
Got it. Thank you.
All right, thanks everyone.